I've explained the case of one principal component. Let's now add a second principal component to this example. So we had principal component 1, that is the line that minimizes the distance between the orange dots and that line. Now the principal component 2, like the principal component 1, has to go through the intersect of the two means. And now the other characteristic is that it has to be perpendicular to principal component 1. So this line is perpendicular to principal component 1. That means that there is a 90-degree angle here and a 90-degree angle there. And that's it. That's principal component 2. Now we do exactly the same measurements that we did with principal component 1. We have the eigenvector and the factor loadings. And in this case, the factor loading is negative 0.49. That's the factor loading of item 1 in principal component 2. And the factor loading of item 2 in principal component 2 is 0.87. Now let's move to eigenvalues, rotation, and variation. Here we first have the representation of the eigenvectors of the two components. Now, what is eigenvalues? So each principal component has eigenvalue and one eigenvalue. What's an eigenvalue? The eigenvalue is the sum of squares of the distance of the values in the principal component to the origin. Let's unpack that. So the origin is the intersection between the two means. So then what we are going to have for each observation, for each of these orange dots, we are going to project them to the principal component. So this orange dot here is projected there in the principal component. That orange dot is projected there. So remember, we use a perpendicular line, not a so perpendicular to the principal component, not perpendicular to the x-axis. So we don't do this, we do this. And here we project this one to there, this one to there, this one to there, and so on and so forth. This one to there, this one to there, and this one to there, etc., etc. So now, after to do these projections, we have a distance between the origin and the observation. So would be the projection of each of the observations in the principal component. Those values will be some of them negative and some of them positive. If we add all these values, we are going to get 0. And we don't want that, because these eigenvalues is a measure of the variability within that principal component. So we need to square those values. We know this trick because it's used to calculate the variance, standard deviation, sum of squares in regression, etc., etc., etc. Then we do the same here. We square those values and then we add all these values. And that is what we call the eigenvalue of the principal component. I'm going to simplify the representation. We had like 30 values, and now we reduce the presentation to only 4 values, 4 orange dots. So what I showed here is the projection of the each of those observations to the principal component. So this one observation is projected there, and I put 1.1, so that means it's the projection of the observation of participant 1 to principal component 1. This one, 1.2, is the projection of participant 2 to principal component 1. 1.3, the observation of participant 3 to principal component 1, and 1.4 is the projection of participant 4 to principal component 1. And for principal component 2, we've got participant 1 projects to principal component 2, and so that's 2.1. Then participant 2 is here, and then it projects to principal component 2, so that's 2.2. And 1.3, participant 3 is here and projects to 2.3 here, and participant 4 is here and projects to principal component 2 here. So now what we do is rotation. Why we do rotation? Well, because here we only have 2 items and 2 components. We can add more items, and it's very difficult to represent those items. The more we add, the more difficult to represent in a 2D in 2 dimensions. So we have to do the maths. But by rotating the principal components, we can add at least one more item. So the rotation, what it does is to put the principal component 1 in the x-axis and principal component 2 in the y-axis. And we've got the now the observations changed the location because they were rotated. Now, another important point we need to calculate is the variation for the principal component. And the variation for the principal component is calculated by calculating the eigenvalue, as I mentioned before, which is the sum of squares of the distances between the observations or the projections of the observations in principal component 1 to the origin. And in order to calculate the variation, we divide the eigenvalue by n minus 1. So now we've got 2 variations: the variation of the principal component 1, the variation of principal component 2, and if we add those 2 values, we got the total variation. And we transform this into percentages, and we've got the percentage variation due to, so the percentage of the total variation due to PC1, and the percentage of the total variation due to PC2. We add those 2 values and we get 100%.